Okay, so now after covering expectation of sums of random variables, and in particular, we looked at how to figure out the expectation of functions of some functions of random variables. We're ready to talk about another very important topic, a set of topics. The first one is covariance, which is related to the variance that we'll be talking about, and might be something pretty new to many of you. But I would imagine the second term that we're showing over here, correlation, might be something many of you have heard about. So for us, we're gonna formally define covariance first, and from which we can derive also the correlation that many of you know it one way or another in the past. Okay, so the definition, okay, so remember here we're working with two random variables. Okay, so we're looking at x and y. Okay, and the covariance, like I said, is very similar to the variance to some sense, except if you remember, for variance we're only talking about for one variable. Okay, so that okay, is talking about like two or multiple. Okay, so to refresh our memory a little bit, the variance, okay, of x is expectation. Sorry about my, expectation of x minus, okay, it's expectation, the squared, right? And then, yeah, so that's what we learned from the previous chapters. Okay, so the variance of x is a expectation in essence. Okay, but in particular, we're looking at the square difference, okay, between any values of the random variable from its mean. Okay, so that's how we define, okay, variance back then. So it's really thinking about deviation from its mean. Okay, so the covariance right now with two random variables, we are really following a very similar idea. So here for covariance of two random variables, we're trying to figure out how they deviate from their means together. Okay, so formally, the definition is also the expectation. Okay, and we have the product in the expectation, which is x from its mean. Okay, and then y from its mean. Okay, so here, as you can see, it's very similar, okay, to in some way to the variance definition that we have looked at before. And just like the variance definition as before, we always, if you remember, in practice, when you try to calculate it, instead of going back to the definition, we are using this simplification. Okay, and back then we derived it step by step. Okay, so just like for the variance, we also have a simple term, okay, simple expression for covariance as well. So let's see how we can get it step by step as well. Okay, so covariance, okay, xy by definition is this. Okay, and then just like what we did back then for the variance, we express the squared term and then still within the expectation. So we worked out step by step. Here we're going to do the same. So you're going to have expectation of xy plus mu x mu y minus x mu y minus y mu x. Okay, and then if you're able to now break it down, so if I add one more step over here, what you have, right, is expectation of xy, right, plus, so here expectation of mu x mu y, they're already expected value. Okay, so you're just gonna have mu x mu y. Okay, and then for the third term, you're gonna have mu y, like I said, is a constant, so you're having this, and then the fourth term is gonna be this. Okay, so when you're writing this way, okay, notice that this, okay, is our mu x. Okay, this is our mu y. So essentially, you plus one copy of mu x mu y, right? But you minus two copies of them. That's why in the end, you have minus mu x mu y. Okay, so in the end, the form is the covariance of x and y is the expectation of their product, okay, minus the product of the expectation. Okay, so see the similarity here, okay, with what we had for the variance in the past. You have expectation of the product, okay, expectation of the square term, okay, minus the product of the expectation, minus the square of the expectation, okay? And actually, like, this is, you can always show that if you're able to know that x and y are independent, okay, from previous video, right? We know that if x and y are independent, this first term becomes the expectation of x times expectation of y. Okay, so in this case, you're going to see that it's going to be 0. Okay, that's going to be something very important. We're going to cover that as a property coming up. But just so you know, many things are connected. So make sure that you know how to do all of those, how they're connected. And I would just also say that, well, if you don't know whether they're independent or not, right? And at the end of the day, this is a expectation of a function of x and y, right? So from what we just learned, if you're working with continuous random variables, then that becomes a double integral of the function multiplies with the joint PDF. right? And then if it's a discrete random variable, it becomes the double sum of these function multiplies with joint PMF. Okay, so that's how you're going to compute it if you're given what they are. Okay, so properties. Okay, like I said, there are many useful properties of covariance, and it will be really useful for us to use some of them as handy tools. So let's walk through them one by one. The first is the covariance of x equals to variance of covariance of y and x. Okay, not surprisingly, if you follow the definition here, or I should say the simplification of the calculation, you will see that they're gonna be the same. Okay, so that's good. And the second one is the covariance of x and any constant is 0. Okay, that is because if you follow that simplification, you're doing x times c, which is a constant, okay, minus expectation. Yeah, my stylus is kind of not working, but let's see. Okay. Okay, and then expectation of c, right? Which, well, is a constant, so you're gonna have c expectation of x minus c expectation of x, which is 0. Okay, all right, and that's why covariance of x and any constant is 0. But also just imagine, right? X is random, right? And c is a constant. So if you think about how they behave or like move together at the same time, it's going to be 0. That's what we mean by the covariance in the first place. All right, and then if you have covariance of x, like both of them are x, that just turns out to be the variance, okay? And that is because, okay, we have, right, the first becomes expectation of x squared, right? And the second becomes, as we know, expectation of x times expectation of x, right? Which is exactly how we compute the variance, and that's why. All right, the fourth one here is the covariance of ax and by is a times b of covariance of xy. Okay, so here we are going to go back again to that simplification of calculation, and then we have ax in the first term, bx is the second term, so we'll just go by step by step. Okay, so here we show it in a few lines. Okay, so here we have expectation of a b x y. Okay, so that's the first term, and the second is you have the expectation of ax times expectation of by, which if you simplify, so remember a and b, they're all constant, so you can bring it outside. Okay, and then that is why in the end you have AB, right? Times expectation of the product, okay? Minus the product of the expectation, which, as we know, is indeed A times B of and times covariance of X and Y, okay? All right, the last one is what if I'm adding a constant, okay? What if I'm looking at the constant a and b added to x and y respectively, okay? So it turns out that the covariance of x plus a and y plus b is the same as the covariance of x and y, okay? So intuitively, think of this, like this is a constant, right, being added to it. And this is another constant being added to it. It's just a constant everywhere, right? And then the relationship, how x and y are deviating from its mean, because when you add a and b to x and y respectively, the mean is shifted at the same value, right? So it's not surprising, let me put it this way, that you won't have any change in terms of the covariance structure, right? And even in the past, if you remember, we talked about when you have variance of x plus a, which a is a constant, it will just become the variance of x as well, okay? So that's another result that we can rely on from before, okay? So the detailed steps is a little bit like not complicated, just like a lot of writing. But at the end of the day, what we're doing, just like before, we're going back to the simplification expression and then do a step by step just to do it very carefully. I'm sure in the end you will get to the covariance of x and y as well. Okay, so I will leave that to you to go through the details, but it's not something very challenging, just really need to be careful. Okay. And now we are coming to also, if you remember, the first topic of this chapter is talking about sum, right? Sums of random variables. And now how about we try to define covariance of sums of random variables? Okay, so I'm showing the result up here just as a starting point. Okay, so what this is saying is that if I have two sums, okay, the first one is about n copies of x, okay, xi. And then the second term is n copies of yj. They all could be different, right? X1 could be different from x2, but generically we're writing n, I guess n terms, okay, n terms of xi. Yeah, let me take that back. It's n terms of xy and m terms of yj, okay, not n copies, sorry. But what we really mean here, as you can see, is that we're interested in the covariance, okay, of two sums, okay? So the right-hand side, this is a general result that is handy to us. So what this is saying is that if you want to know the covariance of the two sums, it is equivalent of getting the covariance of any two pairs of x and y, and then you add all of them up. Okay, so that's what the right-hand side is. You're having the covariance of xi and yj generically, okay? You get every pair and then you add them up, okay? So you're doing a summation over j and then summation over I, okay? So this is one way to, like, say, this is a result given to you, okay? And then we also have a very special case that, like, what we always do whenever you're having anything about covariance, we're always curious about the variance when the two terms are the same, okay? So when the two terms are the same, it becomes the variance, right, just of the one term, okay? And then what we know is that, well, many of this, right, actually n of them, okay, will become the variance of each of the xi, okay? So we have the first term, okay? And then we have the remaining terms, and then mathematically we'll try to write it in a shorthand of 2 times all of the pairs of the covariance when I is smaller than j, okay? And then of course that 2, if you imagine why there's a 2 over there, that is because only here we're considering I smaller than j, right? And then don't forget j could be smaller than I as well, but they are symmetric. So in the end, we just have 2 times the sum of those covariance when I and j like are different from each other. Or if we write it in this way, I smaller than j and then times 2. So that is a special case and could be useful, okay? And even more special cases are this two that I would really highly recommend us to think it through as well, okay? So the first one is, what if I'm doing variance of the sum of x and y? Okay, so remember we talked about the expectation of x plus y, right? That would just be the sum of the expectation. And then for the variance, well, now we are going back to this, right? You have like x and y as the x1 and x2 terms up there. So we know from this result, right, what we have is that you have a variance of x, right? You need to add the 2 variances first, okay? And then you plus the 2 times the covariance. In our case, because there's only one x and y, one copy of y, right? In that case, you only have one pair. So it's 2 times covariance of that, okay? And then also if you're working with variance of x minus 1, minus y, okay? So that is equivalent of doing x plus negative y, okay? So when you do that, right, it becomes, so let me write it in this way, it becomes the variance of x, right, plus variance of negative y, okay, and then plus 2 covariance of x and negative y, okay, if we start strictly from this definition, okay, because what we know is only the sum, right, we don't know the difference, but then of course, you can always write minus 1 as plus negative y, okay. And then what we do, okay, we have variance of x, that's all good, okay. Variance of negative y, actually just variance of y, because it's a constant, right? Multiply, it's a negative 1, multiply in it. And then when we use the result from the variance, this is a negative 1 squared, right? Variance of y, so that just becomes variance of y itself, okay. And lastly, remember the property that we had earlier, when you have a negative 1 here, positive 1 over here, it's equivalent of bringing that negative 1 out, right? So that just becomes covariance of x and y, okay? And that's the reason why it works in this way, okay? And like I said, we have the generic result at the beginning of just talking about the sum of 2 terms, okay? 2 terms of sums, let me put it that way. And we have a special case from the covariance to the variance, and then more special cases when you're working of variance of sum of 2 random variables and the difference of the 2 random variables, both of which go back to the middle special case when we're working with the variance. And then we walked it through it using all of the properties or some of the properties that we covered earlier, which I hope you can follow well. And then later on, when you get to do exercises, all of this will become handy.